session I'll be going through some buffer calculations. In another session I do explain the qualitative approach of buffer action, and so if you are anything like this baby, there is nothing to fear, because buffer calculations should actually be a nice set of marks to obtain. You just have to think through it logically. So I'll give a quick overview again about what a buffer is. And that is a solution that resists changes in pH during the addition of small amounts of acid or alkali. So to reillustrate this again, if we appreciate a weak acid will only partially ionize in solution, so HA would produce H plus and A minus. Not all of it will convert. We are going to assume that the HA concentration, even though it would decrease to produce H plus and A minus, we're going to assume that the value they give us of a weak acid won't change, because it won't change much with the calculations that we are looking at. So we can assume that the HA concentration at equilibrium will be the same as the HA concentration undissociated. So whatever value they give us for HA, we just ignore the fact that it does decrease a little bit when it turns into H plus and A minus. We also have, when we make a buffer solution, its conjugate base. So we have a weak acid such as ethanoic acid or any carboxylic acid, and its conjugate base, in this case the sodium ethanoate, will make ethanoate ions, and this is ionic, so it will 100% convert, and so whatever amount I had at the beginning will then turn into my products in the same amounts, but this will be 100% converted. And because this is going to be all mixed together, then that means I'm going to have a large reservoir of A minus produced. So previously we would have said if we want to do some Ka calculations, then we can assume that H plus and A minus being the same amount would be Ka equals H plus squared, so to speak. But we have a large reservoir now, so the A minus here that the sodium ethanoate produced is going to add to our existing A minus that HA produces as well. But we're going to make an assumption here that the A minus produced by HA is very small anyway, and so any question that gives us the salt concentration or value, then we just assume that that is also the A minus. And so because we have a large reservoir, we can no longer assume this relationship where Ka was equal to H plus squared over HA, and we can no longer assume H plus is equal to the square root of Ka times HA. Any question that says buffer calculations, or where you have sodium ethanoate produced from a reaction, could be from a titration, that with say a weak acid with sodium hydroxide, that would produce sodium ethanoate, we get a buffering action produced. Whenever we have a buffer, we can no longer assume those relationships. We have to rearrange the equation to produce H plus on its own, and we can do that by just treating it as a separate entity, so to speak. So we have to do this whenever we are dealing with a buffer. So we have a large reservoir of both, and in exam questions, again, as said earlier, and whenever a value is given for the sodium ethanoate, just assume it's going to be our A minus. You may have come across the Henderson-Hasselbalch equation. So if we take our standard Ka expression and we take negative logs on either side, then that means we get negative log Ka, and negative log H plus, and negative log A minus over HA. And then by definition, negative log Ka is pKa, and negative log H plus is pH. And so we end up with that relationship, which we call the Henderson-Hasselbalch equation after we make pH the subject. So if we add log A minus over HA to both sides, we then get pH on its own. Or we could appreciate that that is A minus being salt and HA being the acid in question, so you might see that said as well. Or we can have it's a flipped where the acid is on top and salt is on the bottom. Personally, I don't like using these in calculations, but if you're well inclined to work out that relationship, or you are provided in an exam, you just substitute the values where appropriate and know how to convert Ka into pKa, because that's normally given in the question, or vice versa when required. So you can use that if you wish, and I'll give an example where I'll use both type of methods in which you can work out pH. So I would call this an easy question, example question calculation number 1. calculate the pH at 25 degrees, we don't really care about the temperature, of a buffer solution containing 0.05 moles per unit volume of ethanoic acid. That's our HA, which I've highlighted in red. And 0.1 moles per unit volume of our salt, sodium ethanoate. Remember that it's ionic. That is going to be our A-. And then the Ka value, the equilibrium constant for ethanoic acid association, is 1.7 times 10 to the minus 5 at 25 degrees Celsius. Remember, temperature is the only thing that affects the equilibrium constant. So rearranging the equation to make H plus the subject, and simply just adding those values where appropriate. So Ka was 1.7 times 10 to the minus 5, the ethanoic acid was 0.05, and the ethanoate was 0.1. That gives me my H plus concentration, and then negative log that, because pH is the negative log of H plus. That will give us our pH value at 5.07. Should always keep pH to 2 decimal points. If I'm using the Henderson-Hasselbalch equation, which might have been provided, or I've manipulated that expression on the left to have worked it out, then I can just fill it in again. In this case, however, I will need to work out pKa, and pKa is negative log Ka. So remember, pH is how much H plus you have, and pKa is looking at the tendency of the acid to dissociate. So they're two different sort of viewpoints of what makes things acidic. But low values of either would generally mean that you have an acidic solution. So pKa needs to be calculated. So I have to do negative log Ka to do that. And that gives me the value for pKa. So pKa is negative log 1.7 times 10 to the minus 5. And then I just put in all the values that I then have. So negative log of the Ka gives me 4.77. And then 0.1 was the sodium ethanoate, our salt. And then the acid was 0.05. So this one is salt over acid. But if you did acid over salt, then that would have been minus log acid over salt instead of plus log salt over acid. And again, that would give me the same answer at 5.07. So both could be used. Personally, I prefer the one on the left. Up to you. This is another easy question, but it will quickly turn more challenging. So going through this one again. So the acid association constant Ka for ethanoic acid is given by the expression below. The value of Ka of ethanoic acid is that a buffer solution is prepared using ethanoic acid and sodium ethanoate. In the buffer solution, the concentration of ethanoic acid is 0.186 and the concentration of sodium ethanoate is 0.105. If you'd like, you could pause the screen to see if you can then get the value for the pH for this, but I'll be going through it now. So rearranging the Ka expression to make H plus the subject because it is a buffer. Putting in the values as is in the question. So 1.74 times 10 to the minus 5 was Ka. 0.186 was the sodium ethanoate, which I'm going to... the ethanoic acid, which is HA, and that's in blue. And then the sodium ethanoate, which is my A-, that's in red. That's the ethanoate, that's 0.105. So doing that gives me an A+ concentration, which if I do negative log, you should have got 4.51. But this is where it gets hard. So this is where you manipulate the question. Apologies there, where it says in a different buffer solution, the concentration of ethanoic acid is 0.254 mole. Read that properly as concentration there. That's just a bit of formatting. And the concentration of sodium ethanoate is 0.14. So they are my two concentrations, one for ethanoic acid and one for sodium ethanoate. The difference here is I have then added something. So it says here, a sample of hydrochloric acid containing that amount of moles is added to a litre, 1,000 centimetres cubed of this buffer solution. Calculate the pH. So my buffer has now been altered because this one is just a normal one of calculating, and this one is going to be, well, like I did before, but I've then altered it. So taking the expression as normal, finding H plus as the subject, appreciating that the HA is my ethanoic acid and A- is my ethanoate, and then putting in the values, that would give me my H plus concentration. However, I have to appreciate something else has happened here. I have to appreciate that I've added 0.015. So the best way to do this is by applying Le Chatelier's principle. I have added 0.015 moles of HCl to the mixture, and it's a good idea, as I said, to view in the context of H+. So HCl is a strong acid, and normally you'd have to work out the concentration of this, but you wouldn't necessarily need to in this case because it's already in the litre. So 0.015 in 1,000 is 0.015 moles per unit volume of a litre, so that's still irrelevant, and it says you should ignore any change to total volume. So I've added 0.015 mole of HCl. This is a strong acid, so this will ionize completely. So my 0.015 mole of HCl will produce 0.015 of H plus and 0.015 of Cl minus. That means the amount that I had of H plus would increase by 0.015. And when I said earlier, it's a good idea to view in context of H plus and applying Le Chatelier's principle. If the H plus has gone up, then it will need to go down. In order to go down, position of equilibrium must move to the left to remove the added H plus of the 0.015 that has been added to the mixture. In order to do this, my large reservoir of A minus will happily do this. So it will need to decrease by 0.015, and the A minus will have to react with it. So that would also decrease by 0.015. So my H plus went up by 0.015. In order to return it back to, and this is why it's called a buffer, to resist change in pH, in order to get the H plus back to what it was, it needs to decrease by the same amount that was added. So the A minus decreases, and as position moves to the left, because the reaction ratio is 1:1:1, 1 HA makes 1 H plus and 1 A minus, that means the HA value will also increase by 0.015. So my H plus stays constant approximately, and my A minus has gone down and my HA has gone up. I just need to now reflect that in my calculation here to get the value for H plus at the new change here, because it won't be perfect. So for you were to reflect that, 0.251 was my HA. That is going to, as I said, increase by 0.015 because the position moved to the left. And my A minus will decrease. So it was 0.14, that will decrease by 0.015 to reflect the change that the position of equilibrium has moved to the left. Putting in those values, I can then calculate H plus. So using the value for Ka. So 1.74 times 10 to the minus 5 times the new value for the ethanoic acid, HA, divided by the new value for my A minus salt will give me 3.70272 times 10 to the minus 5. All I need to do now is to find the pH, so negative log that. So my H plus concentration is that value. Negative log that will give me a pH of 4.43. So again, to just explain what happened here. So because the HA increased by 0.15, I've reflected that change here. So that is now 0.266. And because my A minus decreased when the position moved to the left, 0.14 minus 0.15 gave me my new concentration of A minus as 0.125. And the reason why I can do the concentration value minus the mole value is because it says the total volume is already a litre. So 0.015 in 1,000 is 0.015 moles per dm cubed. So this is a concentration effectively. But bear in mind that some questions will require you to work out a new total volume. And this question also says ignore any changes in total volume anyway. So it's not a problem in this case. So now it's your turn for the exam question. There are two here. The first one is relatively easy, and the second one is where it gets tough. It's pretty much the same as the first one, but it's 4 marks each. You can pause the screen now, but the answer I will go through now. So the first section all we need to do was just substitute the values in. So I had Ka is 1.35 times 10 to the minus 5, and Hy now, all scary, that is nothing different to Ha. So this is Ha, could be Hx, they do that just to freak you out. So Hy was 0.428, that was the concentration of my weak acid, and 0.0236 moles of my salt. I have to convert that to a concentration, so that might have caught someone out. So 0.0236 in 50 centimeters cubed. My total volume is 50. So I need a concentration for the salt Y minus. So NaY is Y minus. That is the ionic compound that will make the Y minus, my salt. In this case, Y, but in the other example, it was A. So adding all that in will give me a H plus hydrogen concentration of 1.224 times 10 to the minus 5 and a pH at 4.91. So that's the answer to part 1. Part 2 is the opposite as to the example I did earlier, but you might have also needed to appreciate something here, as I did highlight before, and that is to do with how you should view and apply, in context of H+, Le Chatelier's principle. So let's just go through. So from the previous question and also from the information provided, the H+ concentration was 1.224 times 10 to the minus 5. The Y minus concentration was 0.472 because that's the 0.0236 moles in red of my salt in 50. So that was the concentration of Y minus, and my HY, my weak acid, was 0.428, and that was provided from the question. We need to calculate the moles of each of these before the NaOH was added. So moles of my weak acid would be the volume times the concentration gives me moles of my weak acid HY. And my moles of my Y minus would be 50 times 10 to the minus 3 times 0.472 is 0.236, and my H plus would be 6.1 times 10 to the minus 7. The added sodium hydroxide will remove the ones that you added by reacting with it. So H plus react with the alkali, that is added the sodium hydroxide to make water. So viewing in the context of HY, this is dissociating. The moles that we have in this current equilibrium would be 0.0214 of HY, 6.12 times 10 to the minus 7 of H plus, and 0.0236 moles of Y minus. And that was what was said in the question information anyway at the start. So we've added the amount of sodium hydroxide, that was 5 times 10 to the minus 4. And so in the context of H plus, that would mean this would decrease by that value. However, because it's a buffer, it will try to resist the change in pH and thus therefore resist the change in H+. So in order to make H+ back to what it was again, the equilibrium will need to move right to make more H+, returning it to its normal value or original value at 6.12 times 10 to the minus 7. And therefore, if position moves right, in order to do that, the HY must decrease by the same amount because the ratio is 1:1:1. One lot of HY makes one lot of H+ and one lot of Y minus. And then when it moves right, the Y minus would also increase by 5 times 10 to the minus 4 as well. So the H plus returns to normal, so it returns back to 6.12 times 10 to the minus 7, so to speak. And the Y minus is going to be the 0.0236 added with 5 times 10 to the minus 4. So to reflect those changes, the moles of HY after the equilibrium shift will be, so 0.0214 minus the 5 times 10 to the minus 4 would give me 0.0209, and in 50 centimeters cubed, my new concentration of HY will be 0.418. That's important, so I need to use that later. The moles of Y minus after the equilibrium shift, it was 0.0236. I've added 5 times 10 to the minus 4. That gives me 0.0241 moles of Y minus. And you have to remember, this is in 50 centimeters cubed. You must work out the new concentration, and that is 0.482. I now need to just simply substitute these values in. So in order to do that, 1.35 times 10 to the minus 5 times 0.418 divided by 0.482 will give me the hydrogen ion concentration of 1.1707 times 10 to the minus 5. pH is negative log H plus, and pH is equal to 4.93. So if you got 4.93 as your answer, then you have done it correct. Well done. For more support, please check out the other videos. and I'll try to do some more calculations in relation to buffers. Good luck.